Good afternoon. I'm Scott Johnson, President and CEO of Spacely Packets LLC, and I'm here to talk to you today about application layer gateways in the solar system internet. We're going to be analyzing how these systems work, look at an example application layer gateway in the bmail suite, and we're also going to discuss the governance aspects and implications of this technology. So, what is an application layer gateway? An application layer gateway is the component that puts the internet in solar system internet, if I may be so bold. It allows interoperability between existing IP-based services like web, email, SSH, and similar applications, with both remote IP networks that may exist on other worlds or on spacecraft, as well as bundle-only endpoints in the deep space solar system internet network. So, to give you an overview of how this looks, we're going to zoom out a little bit and first take a look at this diagram provided by NASA that shows the Earth, the Moon, and Mars, and several relay components from various providers. Let us consider that on the Earth, there is the terrestrial internet. This is not expected to change. What we do expect to change is the growth of IP networks on the Moon and on Mars. Eventually, wherever we go, it is likely that we will build an internet-like IP network. This leaves us the challenge of connecting these networks to the terrestrial network, the original internet. To do so, we use an intermediary network called a bundle protocol network, which has delay and disruption tolerant properties that are enabled by a store and forward mechanism, which gives us the opportunity to overcome the high delays, the high latency, and the disruptions in end-to-end network path that are generally the condition in space networking. But as we look at this diagram, we should also consider that this bundle network is not only space nodes, it also includes on those internet segments an overlay which allows end-to-end bundle connectivity from the terrestrial internet to the Moon. We can leverage this end-to-end connectivity with application layer gateways to enable many of the services that we enjoy on the terrestrial internet in an interplanetary or solar system fashion. So we're going to examine bmail, which is an example application layer gateway for SMTP, the Simple Mail Transfer Protocol, to enable solar system-wide email service. As I said previously, this allows us to connect free-ranging spacecraft, the terrestrial internet, and a lunar or Martian internet. That's small I on the later internets. We use capital I to designate the internet as we know it. So what components does bmail have? Well, it requires all of the following things in order to complete delivery of mail to remote worlds or remote spacecraft. The first is the domain name system, both recursive and authoritative functions, as well as root functions in some cases. What this does for the neophyte is it translates domain names such as www.foo.com into a numbered IP address such as 12.13.14.15. This prevents us from having to remember long strings of numbers in order to connect to things, and I will make the case that while this is crucial on the terrestrial internet, it's just as crucial on the interplanetary solar system internet. We also use a mail transfer agent, an SMTP server, MX, a mail exchanger, or an MTA, as they're variously called. They all refer to the same mechanism, which is the server that hosts the mail for a particular domain or set of domains, and then provides service delivering mail from users of those domains to users of other domains, and vice versa. We will require, if to participate in a bundle protocol network, we will plainly require a bundle protocol agent. In this case, we use ION, the Interplanetary Overlay Network, delay-tolerant networking suite, originally developed at the Jet Propulsion Laboratory. Finally, we have to tie the latter two components together, and we use shim applications for that to interface the bundle protocol agent and the mail transfer agent. DNS lookups are ancillary but necessary components of this process. However, there is no direct interface necessary between the MTA and the BPA beyond, or between the MTA, the BPA, and the domain name server beyond that which would normally be required for a DNS lookup. So our shim applications interface the BPA and the MTA. We have bundle mailer, mail bundler, and the bmail control script. Bundle mailer and bmail controller run on a receiving host or node, and they process inbound bundles into emails that are delivered to a user over a standard Internet Protocol-based SMTP network. There's also mail bundler, which is the part that accepts a mail from a terrestrial user or a lunar user or a Martian user, as the case may be, and turns that into a bundle payload that is properly, which has the proper syntax for acceptance on the remote end. So, as I've stated, naming of network hosts is kind of a key aspect to human interaction with the internet. It's easy for machines to remember numbers, but it is not so easy for humans to remember numbers. We do much better with things like names, and so we have a naming convention called the DNS for the public internet. This case remains true for the solar system internet, and thus we must extend the DNS capabilities in order to perfect a solar system-wide DNS system that functions interoperably across vast distances. Here you see a diagram of how such a system works between the Earth and Moon. This is a reasonably complex diagram that details the entire algorithmic state of a mail application which also uses the DNS to perform its function. At this moment, we're going to focus on the DNS components, and I will simply point out first that there are two discrete DNS networks represented here. On the left, there is the terrestrial DNS network, the one we know, love, and use on a daily basis. On the right is a lunar DNS network, which is isolated from the terrestrial DNS network. It provides local DNS services on the Martian surface to overcome on the lunar surface rather, to overcome the delays that are associated with moon to Earth communications. Now, these delays are not so great, but we want a system that scales and can be easily replicated in mode and functionality as we expand further into the solar system. As such, we can refer to these off-world DNS systems by their locality, lunar, Martian, etc. And we can also recognize that there are intended to be multiple discrete DNS systems running at any given time in a solar system internet. The way these things handle data is a little bit different than the normal DNS system. Simply in the way that we populate the zone files with the information that is to be distributed through the distributed database of the DNS system. In particular, we don't want to have any off-world IP addresses registered in any DNS system. And so we would put a moratorium on A and AAA records representing IPv4 and IPv6 networks, respectively, for those domains which represent off-world assets. So anything on the moon would be an off-world asset to Earth, and anything on Earth would be an off-world asset on the moon. You'll notice with the color-coded lines that no DNS lookup leaves its own network. There is no need in this architecture for a transit of deep space or a bundle protocol network with a DNS query or response. Now we're going to look a little closer into how to configure bind9 as a name server to provide this function, both on a terrestrial network and an off-world network. On the left, you will see the configuration file, etc. bind named.conf.default zones that exists in every implementation of bind. This is a normal configuration file, and you will note that the root zone, or zone open quote dot close quote, is represented by a hint record that is in a local file. To contrast, in an off-world name server, you will notice the root zone is a master type zone, and it has the root zone data local to it, calling a different file. This is because the hints, the root hints file contains information on connecting to the distributed network of DNS servers on the Earth as a IP-based transaction. However, this IP-based transaction is not going to be possible from remote worlds, so we must replace that with a local file that provides us the information necessary to find the application to remote worlds. Represented here on the left is the user shared DNS root.hints file referenced in a normal DNS operation mode of operation. And you will see that it holds the addresses of A, B, C, etc. root servers, both IPv4 and IPv6 records. Conversely, on the right, we see that we are simply defining name servers for all of our top-level domains that we wish to support. And this is a truncated list here because it's not quite yet necessary to support the entire list of off-world domains in a simulation environment, as well as indicating that the name server for all of those off-world domains is indeed the same server that we are working from, the local name server that is both authoritative and recursive for the lunar network in this case. You'll also note, if you're a student of history of the internet, that 3FFE::1 is the IPv6 address for luna.sol.int, meant to represent the lunar network application layer gateway. 3FFE is a very special address block in IPv6. It was used in the 6-bone for network testing before the production IPv6 network was stood up and has since been retired and replaced with production address space. I use it here as a nod to that history and as an indication that there are governance issues which need to be attended to concerning the allocation of off-world IPv6 resources, among others. The next configuration file we have to modify in bind9 is your named.conf.local file in your /etc/bind directory. On the left, you'll see a normal configuration of a authoritative name server, which is publishing several domains into the public DNS system. This is how it normally looks. On the right, you will see the named.conf.local from luna.sol.int, which specifies as master zone all of the top-level domains listed. This allows us to take DNS queries and return results pointing to application layer gateways. This is easier for email because we have the MX record in the DNS system to specify mail exchangers. However, we can use a CNAME pointing to the domain name of a application layer gateway, which supports other services as those services are developed. So on the left, we have a terrestrial DNS lookup of an application layer gateway for an off-world domain. Here we ran a dig query on luna.sol.int. We show no A record, meaning there is no IPv4 address listed in the DNS to match this domain name. For space purposes, I didn't show an AAA lookup. However, I promise you, if you do one, you will find that there is no IPv6 record for this domain either. We do, however, have an MX record, which points to durga.spacelypackets.com, the application layer gateway that is directly to my left here off camera, and I'm sorry I won't be able to show it in this video. So this is what it looks like when we try to look up an off-world domain. We get the MX record, which allows us to send mail to durga.spacelypackets.com, which is set up to process this mail and deliver it into the bundle protocol network. On the right side, we see the contents of several of the top-level domain zone files in an off-world name server. So you can see here that we have, beginning with .org, and all of these are reasonably similar with the exception of .int, which actually names numbers luna.sol.int with an IPv6 address. But most of these are simply wildcards that point to the application layer gateway. The wildcard represents any record which does not exist, and in full operation, this might not be a wise process, but the mechanism exists if it is necessary. That's basically all we have to do for the domain name system. We configure it in that fashion, we restart, and we have a functioning off-world capable DNS system, or DNS server rather. This allows us to do lookups that return results pointing to an application layer gateway, although multiple application layer gateways can be designated in this fashion, each with different domain names or in a round-robin fashion with the same domain name. Our next component is the mail server, the mail transfer agent. As I said before, this is the part that connects, or that listens for email from other mail servers, accepts them, and delivers them to a user's mailbox or spool to be retrieved. It also will connect to other mail servers to deliver a user's mail to a remote domain. As I said previously as well, this is not exactly cut and dried for off-world operation. So we need to add some things to the mail server in order to be able to make it compatible in a solar system internet fashion. So here we're going to look at some of the configuration files of XM4, which is the mail transfer agent we chose for our networks. There are two key components that need to be added, and a overall configuration that needs to be set. The overall configuration that needs to be set is this. The mail server must be set to accept email for a domain which it intends to act as an application layer gateway for. So, in our example, durga.spacelypackets.com, which is the application layer the terrestrial application layer gateway, is configured to accept mail for luna.sol.int because it understands that it is to process that mail further, and so it treats it as a local domain. The two specific configurations that are required inside the mail server are custom router and transport declarations to handle the processing and delivery of the off-world mail. On the left is the configuration for Durga. On the right is the configuration for Luna. You can see that on Earth at Durga, we accept mail for luna.sol.int, and we transfer that to a specified named pipe, the IPN2 pipe transport that will handle this mail. The transport executes the command user local bin mail bundler and then the IPN node number and the EID of the listening service at luna.sol.int. We use batch mode SMTP, and it's important that we set the user and the group of this transport to the user of ION on the local instance, on the local host. Fundamentally, what happens is the mail is output from the mail server with the Unix pipe into the mail bundler command, which then accepts it and bundles it and sends it into the bundle network. On the right, for the configuration for Luna, we are accepting mail for everything but luna.sol.int with this particular router. The transport configuration is very similar, and I will not go into it in further detail, except to say that it is important to make sure that you have the EID correct and the node number of the EID correct that you're attempting to deliver to in order to perfect your connection. That's all we need to do for the mail server. For the bundle protocol agent, there is one other part to the terrestrial and off-world mail server configuration, and that is to edit a file in the XM configuration directory router section that handles local delivery. We need to eliminate the check local user. This will make sure that we don't have to have the same batch of usernames on the delivering mail server as we do on the eventual off-world receiving mail server. Finally, the bundle protocol agent. This connects the local bundle protocol node to the larger store and forward delay and disruption tolerant network. This is the key advance that allowed reasonable networking to happen in high latency and disrupted path environments. Here we see the run control files, the configurations that we set to perfect the connection between these two bundle protocol enabled hosts. One specific necessity for the delivery of, or for the use of the bmail suite is to have your ION configured to support DTPC, or delay tolerant payload conditioning. And if you can imagine this as if a BP network is analogous to a network, an IP network in the network layer, then DTPC would be roughly similar to TCP/IP in a internet, or to TCP in an internet protocol network. They are both transport layer protocols, and they both provide reliability services to the data that is being transferred across the network. So, this is a full working configuration file. It is very simple. One of the simplest is just two nodes. There is no BPSec enabled. This is primarily because these two nodes are connected via 10 gig fiber interfaces directly cross-linked, and so it's going to be kind of hard to tap this. Notwithstanding, it is intended in a production network that a full BPSec implementation be applied here, because these are, after all, wireless signals and subject to interception, capture, and analysis. And if those are encrypted strongly, that makes that process much more difficult. That's it for the BPA. Very simple configuration for ION. The shim applications, which connect these two, enable internet, are kind of the Legos that we had to make, as opposed to the Legos we could simply stack together in order to perfect solar system internet mail delivery. Jump back to this diagram for a moment. In the larger bubbles to the bottom, in the middle column, you will see the two shim applications at work, mail bundler and bundle mailer. These are the place that they reside between the bundle protocol agent and the mail transfer agent. Here is some of the code for bundle mailer and for mail bundler. This is all open source code distributed under the GPL version 3 license. We encourage you to use and expand upon it, and we would hope that in the process you would be willing to share any improvements that you make to the code base back to the community, so we may all enjoy a standardized implementation. Speaking of standardization, we do have 2 active internet drafts. If you go to datatracker.ietf.org and search for Interplanetary, I believe they're the only 2 drafts that will come up representing the Interplanetary DNS or Solar System Internet DNS and Interplanetary email solutions. These are living documents that are under revision at this time. And I encourage you to review them and provide feedback to the DTN mailing list at the Internet Engineering Task Force. This is simply an implementation of what we hope will become standardized procedures. The final component is the bmail script. Eventually, I would probably like to move this into a C program, but for observability and ease of initial deployment, I left this as a Unix shell script. Basically, this is a loop that runs bundle mailer, which listens on an EID for incoming bundles. When it receives an email payload, a bundle payload that contains an email to the appropriate EID, it will first echo that to the terminal that this is running in. That's for production operation, that should be commented out. But for testing and integration, it was a very handy tool to determine if our data was passing correctly or not. And then we send that mail via a Unix pipe into the XM mail server, which treats it as a new mail that is generated locally on that host and delivers it either to the local user on that host or to an IP-connected mail server elsewhere on the off-world network that we have connected. I will note here that there are differences between these 2 files on each host. One is using topic ID 26, the other is using topic ID 25. This is to allow a duplex circuit between a given pair of mail servers. One listens on 25, the other listens on 26, and so one must talk on 25 and one must talk on 26. This is configured inside the bundle mailer source code, so you must be careful to set the correct sending topic ID when you compile your bmail suite on each node. Now, when we put all of that together, we can send email back and forth to the moon. We can send email back and forth to Mars. We can send email back and forth to New Horizons. We could send email back and forth to Alpha Centauri if we had something there to listen and to respond. This is what it looks like all running. On the top left, we have a network monitor on Durga showing us ingress and egress rates. We have some code of the IPv6 convergence layer adapters on the bottom left. We have process monitors in the middle 2 bottom terminal windows. The middle two top terminal windows show us the bidirectional data flow, the echo to terminal that I mentioned in the bmail script. And on the right, we see two email boxes that have been in active use for some time now on luna.sol.int. This is my operations console, shall we say, for extended testing and proving of these software systems in a live environment. So, how does all of this relate to governance? Well, there are quite a few resources that need to be managed in this model. As I previously stated, there is off-world IPv6 address blocks and the allocation thereof, and who performs that allocation thereof. At present, this is vested in the RIR system, which manages terrestrial IP addresses and autonomous system numbers as well. It is worth noting that it would be very handy to have dedicated blocks allocated by IANA to the RIRs in this scenario for off-world use, such that they would not be routable on the terrestrial internet by convention. Similarly, autonomous system numbers need to be allocated for multiple operators interacting together in an IP fashion on the lunar surface as the pressing need, and on other off-world surface networks as time passes. This is not really a difficult problem. There needs to be uniqueness to these numbers. Ideally, we would have uniqueness to off-world ASNs as well, so that one ASN would not exist on Earth and on the Moon, for example. But as a matter of practical operation, it's kind of irrelevant, because since the two networks are not routing packets to one another, there is no chance for conflict or collision in these scenarios, unless someone tries to make an end-to-end IP link. Notwithstanding, it's probably wiser to have these resources be unique universally as opposed to globally. Next, there are domain names designated for off-world resources. At present, we use sol.int, which was allocated to the CCSDS as an international treaty organization for the naming of off-world domains. While this solution is functional, viable, and governable, there has been an expressed proclivity in the market toward shorter, more descriptive off-world domains, such as .moon or .mars. Who would manage those domains is a governance question. In my humble opinion, this should be left to a nonprofit organization in a similar fashion to the way that PIR manages .org. This would allow a multi-stakeholder governance model to cover the operation of the top-level domains as well, ensuring a fair and level playing field far into the future for these resources. Those are the IP-based resources that need to be managed in one form or another. And there are several bundle protocol specific naming resources as well that require governance at present or will require governance in the future. First among these is the Bundle Protocol Interplanetary Networking IPN Naming Scheme Default Allocator Node Numbers. These are presently managed by the IANA, the Internet's clearinghouse for protocol-specific registries. When those registries become significant enough that they require more management than a simple registry, then we wind up creating things like the RIRs and ICANN to manage IP addresses and ASNs, and domain names, respectively. Notwithstanding, these it would be preferential to have these managed in a multi-stakeholder fashion. As well, the bundle protocol IPN naming scheme allocator identifiers. Finally, there is a development, technical development that is occurring that will require a registry, and that is interregional forwarding for the bundle protocol. The concept of regions is somewhat analogous to the concept of autonomous system numbers in an IP network, in that it would be used to designate a administrative domain or a scope of operation for a particular network operator when you have multiple network operators that are interacting together to form a network of networks. Gone are the days of governments being the only operators in space. With the ease of deployment of CubeSats, the lowering costs of launch, and greater interest in space exploration, there are now a wide variety of stakeholders at the table who, in order to meet their requirements as commercial entities, need to have clear guidelines as to how to proceed, such as we do with the terrestrial internet. There are well understood procedures for the acquisition of domain names, top-level domain names, IP addresses, autonomous systems numbers, and these are the primary resources necessary to interconnect at a network level on the internet. A similar clarity of purpose or clarity of method would be highly beneficial in the growth of the solar system internet, in my humble opinion. I'd like to thank you all for your time today. I hope my talk has been informative and entertaining. You can contact me at scott@luna.sol.int if you have questions as to the contents of this talk or how to implement some of the technologies that have been described. Until then, I will leave you with this thought. Bundle up. It's cold out there.